Okay, welcome to my today's talk about imitation learning. Since I did an essay rotation, I did a lot of literature research, and instead of talking a lot about robotics, I will concentrate on the imitation learning part and give you a little introduction. So we have less topic about robotics, but in the end I will add some examples. So let's start with a refresh of reinforcement learning. So in reinforcement learning, we usually have an agent and an environment. The agent can interact with the environment by actions and observe rewards and states. So the goal in reinforcement learning then is to find a policy, pi star, that gives us for a certain state the optimal action such that we get the best reward for our task. But in contrast to that, imitation learning, we already have this expert given. The expert already solved this problem. And now we want to find a policy, given demonstrations from the expert how to solve it, such that we find a policy for our agent that approximates the expert policy. Let's just dive in with the first category of imitation learning, behavioral cloning, and a very naive approach, supervised learning. So let's assume our task is to play Mario Kart, and we already have given a nice expert that is really good at playing Mario Kart and gave us some demonstrations. So for every task, for every state, he gave us already actions that we have to do to drive through this track perfectly. Supervised learning would be that we just take, that we find a policy that minimizes the error between the demonstration he gave us and our policy. So if everything goes well, our policy now is as good as the policy from the expert. So everything is solved, right? Like we can just drive through the track perfectly. Well, let's assume we train our policy given from the expert and we start driving. And now someone appears and throws a banana right into the track where we would drive from our policy. We would crash into this banana. That is not good. Mamma mia. So we're now in a state where we don't know what to happen because the expert did not tell us what to do in such a state. This is the so-called uncertainty of environment. And in imitation learning, this is the main problem, the so-called covariate shift problem. So the shift between what we learned, what the expert gave us for demonstration and what we actually learned. From our current state, we basically don't know how to continue. So we will probably do some random actions that could go well and we continue the path, or we just crash again. So that's a problem. How could we tackle this problem? So wouldn't it be nice if we always have the expert with us and ask him, hey, which actions can we do as soon as we get into a state where we don't know how to continue? So for example, we're in an unknown state ST and we're like, which action should I take? The expert tells us, yeah, take action AT. In state ST1, we ask him, which action should we take? Action to AT plus 1 and so on and so forth. Now let me introduce you to the first algorithm that basically combines the supervised learning approach with this interactive imitation learning approach. This looks a little bit abstract, it's just a code, but let me go through it. So let's assume we train our agent by running labs. We just drive through and through, and for every lab, there is a certain probability BI where we either take the policy that we already learned with probability 1 minus beta I, or with probability beta I, we ask the expert, hey, what can I do? Then we sample the trajectory, so we drive a lab, save the data, and in the end, train the classifier on all the data we sampled so far. This whole algorithm only converges if the sequence of beta i's converge to 0. So let me give you an example here. For example, if we're in ST plus k in this state, and assuming our beta is 0.5, then we basically randomly ask either which action should we take? And we either get an answer from the policy that we already learned, or if we arrive in the next state, we get the action from the expert. As you maybe saw in the algorithm, for the first labs, the beta I is very high. So in the beginning, we will ask the expert a lot. This is a problem. Wait, let me get you this later. This is a problem because that in one level of learning, 30 frames per second, where one round takes 45 seconds, the expert only for the first round has to label 1,350 states. And this is a lot. The expert would get exhausted at some point if we assume that this is just a normal human being. So let's jump to the results of Dagger. So they used this algorithm Dagger that I just showed you on Super Mario Brothers, where the goal is to just finish the level. What we can see here, the important two graphs are the blue and the red one. And what we can see here, giving a certain number of training data, the more training data we get from the expert, the better our Dagger dataset aggregation algorithm compares to the supervised learning algorithm. So we already improved our policy in comparison to the supervised learning task. The problem that I just mentioned, that the expert is asked a lot for the states, will be solved by some extensions. For example, we have two, I would say, broad areas, robot-gated and human-gated interactive reinforcement learning. In human-gated, we have the expert as observer. So the expert only intervenes when we reach, or when the agent reaches a state where some critical failure could happen. Robot-gated, on the other hand, asks explicitly the expert for advice if he reaches a state where he is, for example, in a critical failure state. So let's then go to the second big topic of imitation learning, inverse reinforcement learning. So I showed you in the beginning how normal reinforcement learning works. In contrast, inverse reinforcement learning now wants to infer the reward function that the expert was trained on, because we know the expert already has solved this task, and now we want to know on which reward function the expert got trained on, such then afterwards we can train our agent with these rewards with normal reinforcement learning. The problem here is the first inverse imitation learning algorithms were all very computationally expensive, because we have to solve for every iteration step the whole MDP, or the whole reinforcement learning problem. Means we have to train our agent until convergence, then we update our reward function, and again and again. This is very computationally expensive. And another problem is we have reward ambiguity, means multiple reward function can lead to the same policy. For example, if we take the normal, a random reward function R of SA and just multiply it by C, then we get infinitely many reward functions that would all lead to the same optimal policy. Let me introduce you to an algorithm that solves both of these problems, called generative adversarial imitation learning. I will not go into the code again, but give you a more abstract view of the algorithm. So assume we have our agent A, our expert E, and some discriminator D. The task is now to fool the discriminator that the trajectories, or the trajectories that we drove through the track cannot be distinguished from the expert. And how do we do it? So in the beginning, we start with a set of expert demonstrations. The expert, we have the set of expert demonstrations. For example, here a lot of a lot of labs. We initialize a random policy from our agent with just random values. So we can start with at least something. The next step then would be to just let our agent drive and sample some trajectories. Since it's a random policy, we might crash very often and we don't get very far in the track. The next step would then to collect what we just got from the agent, and we collect what we have from the expert. We sample these both data points and train our discriminator in a simple supervised learning task to distinguish these two, to distinguish between the agent and the expert trajectories. Then, after the discriminator was trained, we now get a reward back from the discriminator by training our agent. And the reward is now how good were we able with our trajectory to fool the discriminator. So if our reward is high, then our discriminator can basically not distinguish if we are an expert or if we are just like ourselves. After that, with these rewards, we take some TRPO steps. That's trust region policy optimization that they used in this paper. And we do some steps with that. And then the whole iteration begins from step one, where we sample our trajectories, train our discriminator, and we do this until we find a optimum. So how could this look like? In the beginning, we just have our policy that does basically nothing, and for every step, we get closer to the expert trajectory until we're approximately there. Here are some examples from the OpenAI Gymnasium dataset that are like I don't know if you know them, but these are like similar to these Atari games, where they, for example, in card call, have to balance a stick on a card such that the stick does not fall over. And here we have different tasks. You can see in the dotted lines here are always what the expert gives us, like that's the optimal policy. The green one are the random policy. And what's important here is like, ignore the yellow and the violet, the yellow and the purple graph. We're only interested in the blue and in the red one, because the red one is behavioral cloning, what I showed you before. And the blue one is the Gale. And as you can see, for every task, Gale performs better than behavioral cloning, what I showed you before. Still, Gale has some limitations. For example, it's very sample efficient. Because we have to train this discriminator, we have a very sparse reward. And because the discriminator, so the reward signal, changes over time, we have what's called moving training dynamics. So the reward is not fixed. We have lack of interpretability because the reward function gets implicitly trained during the algorithm. We have less generalization to new tasks. And since this is similar to generative adversarial networks, we still have the same problems from GANs like mode collapse, oscillation, or vanishing gradients. Other inverse reinforcement learning problems I have listed here just to show you that there are also other things and other methods to solve. Gale is, for example, maximum entropy method. We also have maximum margin methods and Bayesian methods. I will now get deeper into that. What I found most interesting during my lab, during this essay rotation, was diffusion policies. So you might already heard of picture generation, and this is done by diffusion networks. So the goal here is we have a data set with pictures, for example, and we gradually add noise for every step until these steps we added noise. the goal now is to train a network that reverses this noise. So this network basically goes from T as input, xt1, and removes the noise step by step until we are back to our input picture. So the same principle can also be taken for the trajectories that we try to find. For example, the task here is to place this T into the underlying T, so they overlay. The idea here is the same. We start from a random noise, and by denoising the random noise, we get a path that basically solves our problem. Keep in mind that the training data for diffusion policies is not very, so we need a very large lot of expert data here, so the diffusion works. We have long inference times, which means it's not very suitable for real-time applications, and we have no exploration like Gale that I showed you before, or other inverse reinforcement learning. Some advantages, though, are they are superior in handling multimodal actions. What I told you in inverse reinforcement learning, we always have different kind of reward functions that give an optimal way. Here, this also means we have different paths that we can take to solve our problem. And it's very good in choosing these paths to not get confused. The training is all more stable, and it's robust to perturbations. If you, for example, hide your camera, if you obscure the camera with your hand and the whole picture is not visible. So in the end, let me show you two examples from imitation learning with robotics. The first one is called adversarial motion priors, where they basically used Gale and combined it with a reinforcement learning task. So we not only have the reward return from the discriminator, but also the reward from our environment. And here, for example, you can see that we can change our direction by giving normal walking examples. Here, we can also have different kind of locomotion, like a zombie walking, and we can also change the directions. Or if we have example clips of making a cartwheel, we can extend this to make cartwheel over rough terrain. The next and last example I want to give you is learning agile skills with adversarial imitation of rough partial demonstrations, where they basically try to solve the problem. How can we imitate a motion if the demonstrations that were given by the expert are just partially? For example, here you can see that the demonstrations were just by turning the body of the robot without the robot knowing what exactly are its joint position or velocity. And they were able to, from this demonstration, to create a real back salto. And here are other locomotion examples, for example, hopping, or I would say a wavy motion. Yeah. This can also be transferred to other robots, so it can be transferred to other robots with these examples. If only I had more time, I would tell you a lot more that I encountered in my essay rotation, but so far I will thank you all for listening.
Really cool talk on the last example. Here, I know that in in deep learning, or probably deep RL probably too, a big problem is catastrophic forgetting, so transfer learning, where you try to, I don't know, train a network on one task and train it on another task, and it's able to learn this one task, it's able to learn the other task, but if you put it to the original task, it's garbage. And or like it struggles to then like maintain what it has learned previously.
Yeah.
Here, if you then kind of demonstrate these individual things, can they then maintain that, use it somewhere else, but then also learn things on top? Because that modularity would make it really interesting, right?
So you're asking if we, for example, teach him how to walk, if he can not only walk on rough, flat terrain, but also on, I don't know, over hills or something.
Yes, and if he could walk and jump, for example, because if it was like not domain specific, but you would kind of, because ideally you would want a robot to do both, right?
Yeah.
Walk over different terrains, and then if there's an obstacle, jump over it. I don't know, with that backflip or so.
So they did not train this here. So this was very domain specific, as you can see. Like here, they try to make a backflip. So what they can do here, and the idea here is that we can use this demonstration with some, I don't know, body, jaw or orientation, and use it also on other robots, right? Yes. But they did not investigate how the other way, like there is no additional learning in other environments. So I can't really answer your question for this paper here.
Yeah, I mean, it just seems like a difficult problem to do this, but in a very general way.
Well, I know, but what I can tell you, so for another example, another paper I read where they tried to, where they trained the robot to climb downstairs, a ladder, sorry, not stairs, a ladder. It also happened that because the reward is high, he just jumped down from the elevated position, which is not good because there are robots that are 50 kilograms or something, and they just break. So yeah, that's the point.
I have a question about the intimate learning, and particularly if you think of a realistic situation that probably you're learning basketball or learning to drive from your coach, you probably don't really have the exactly observation of your coach at the same time. Like you don't really in your coach's body to have the same kinematic feeling perceptions and etc. So like, but does that make a difference? And also, is there any agreement considering that you have a pretty limited preserved instruction from your coach instead of full image?
Exactly. So this is here, discussed here, imitation from observation, which basically discuss what can we do if we don't have the actions, but only the state of the person. For example, there are also papers where they learned playing Atari games just from YouTube videos. And in YouTube videos, you don't have the actions, you can only observe the person. But yeah, this is definitely also possible. There are also algorithms for that. For example, GAL-FO, which is Gale, but from observation. And yeah, this is possible.
Very interesting.
Yeah.
Really cool talk. I had a question about the first case of imitation learning that you presented. You said in the end that it's a problem that there's an ambiguity of the reward function. I didn't quite get why this is a problem.
So the problem with ambiguities of reward function is the following. Let's say you have a reward function that your expert got trained on, and now you have another reward function where, for example, in a state that the expert did not observe, we have a very high reward or a very low reward or something that is not covered by the expert. So we do not want to make assumption about the environment except of what the expert did. So that's why we have to maximize the entropy of the policy such that we really only care about what the expert did and try to do as many assumptions about what else is going on. So this is why it's important, or this is why we have an ambiguity, because we can have reward functions that have some high rewards in areas where the expert did not even go, or yeah, that would be a problem for learning later then. Does this make sense?
Yeah.
Okay.
Last question.
So at the very beginning, you had these, you describe something like human gated, where the expert decides when they intervene.
Yeah.
And I was just wondering on that, it seems for me like a very difficult problem to know when to intervene, because if you just do something like what you later had with the discriminator, where you say, well, when does it deviate from the expert or so, that would happen too often, right? So you'd need to kind of learn a good policy as the expert on when to intervene, and is there any literature on how that timing is this, or like how that moment is determined?
Now about
human gated dagger.
So
yeah.
Usually human gated means we observe it, and we already know when a failure happens.
Right.
For example, if someone falls down while running, then we observe, okay, yeah, he just fell down. But the other way around, what you just, I think your question does more relate to robot gated, because when does the agent know that he did a mistake, right?
So human gated means like literally human in the loop.
The human in the loop, or some other kind of expert,
yeah.
Right? But robot gated means, okay, the agent, for example, crashed into a wall. This is a critical failure. How can we prevent this? And for that, we have other policies, for example, or distribution functions that tells you how much you deviate from the expert, and then says, okay, we deviated too much from the expert. Now, please intervene. We don't know how to continue.
Thanks.
I had one question about the results you present for the Gale method. I think I didn't quite get the plot, like on the x-axis. Is this training, since it starts already very high?
Yeah, so this is number of training.
Not those. For Gale.
Oh, sorry.
Sorry.
My problem.
Yeah, those. What's the x-axis?
X-action is the number of expert demonstrations.
So why does it start already so good, the GTEL it's called up method? Why isn't it starting at 0 like?
Because as I already told you in the if you have a very good discriminator at the beginning and he gives you good rewards, you can already in the first iteration start training a really good
So you start at the beginning of the trial, you bet, but till you're done one round, you're already good.
Exactly, like
Okay.
not one round, but until convergence of the whole GAN. So it starts at 4, as you can see here, and that's what I meant. I think I didn't say it. Oh no, I didn't say it. Okay, but the advantage of Gale is that you don't need a lot of demonstrations to get a good result for the expert. That's why we already, for example, in Cardpool, it is enough to give our whole network one demonstration and then let the network converge. Exactly.
No more questions here. I would like to use the last minute to thank Georg, because you joined us earlier than expected.
Thank you.
Thanks a lot.
Yeah.
I think
Good.
you listened to most of the talk.
Yeah, I was missing to most of the talk. Well done. Really nice. Yeah. Cool.
And thank you to you too for
Yeah.
the ability to do my assertion.
So, to both of you, Georg, yeah, thanks a lot for this final talk today. Thank you. Thank you.
See you guys. Bye.
And I see you again tomorrow.